Welcome to this explainer. If you've ever looked at a raw circuit board and just felt like you were staring at some kind of alien language, or maybe you've got this idea for a brilliant gadget but absolutely no idea how to actually build the thing, well, you are in exactly the right place. Today, we're taking a really fun, hands-on journey into the actual mechanics of creation. And our ultimate blueprint for all this? The absolutely massive, totally definitive textbook, Practical Electronics for Inventors.
Written by physics and engineering heavyweights Paul Scherz and Simon Monk, this book is straight up legendary in the DIY electronics community. But here's the thing, it's huge. So our goal today is pretty ambitious. We're going to take the absolute core concepts from roughly 400 to over 650 pages of incredibly dense, brilliant material, and we're going to pack it all down into a manageable, highly effective toolkit. A toolkit you can actually use to start inventing.
Okay, let's dive right into this. And yeah, I know exactly what you're thinking looking at something like this. It looks completely terrifying. It's just this massive wall of squiggles, lines, and strange geometric shapes. But hey, don't panic. What we're really looking at here is simply the alphabet of a completely new language. It's like learning to read for the very first time. Once you understand what these specific symbols actually mean, that whole wall of noise just transforms into a set of perfectly logical instructions. And we're going to decode that alphabet together.
So here's our game plan for today. First, we'll tackle the language of electronics. Second, we'll get into semiconductors and microchips. Third up is optoelectronics and sensors. And finally, we'll wrap things up at the inventor's workbench.
All right, let's kick things off with Section 1, the language of electronics. It is time to decode the basic alphabet of circuits. So when you really break down electronic parts, they generally fall into two main camps. On one hand, we've got passive components. Think resistors and capacitors. These are basically your simple traffic controllers. They don't generate any new power, they just resist, store, or filter the electrical current that's already passing through them. But then, on the other hand, we have active components, like transistors and integrated circuits. Now these are the dynamic brains of the operation. They can actually amplify signals, act as logic switches, and ultimately allow your circuit to make real decisions.
But that begs the question, how do you actually know what a component does just by looking at it? Well, that brings us to component labels. Because honestly, these parts are often smaller than a grain of rice, so manufacturers obviously can't print a whole instruction manual on them. Instead, they rely on a clever translation code. We're talking tiny colored bands, specific letters, or short little digits that tell you a component's exact value, its tolerance, and its physical characteristics.
Let's take resistors, for example. You're going to commonly see a 4-band color code on these little guys. The rules are actually pretty simple once you get the hang of it. The first 2 bands give you the significant digits, the third acts as a multiplier, and that 4th band tells you the tolerance, which is just a fancy way of saying how precise that resistor actually is. Oh, and if you're dealing with those modern super tiny surface mount resistors, they usually drop the colors entirely and use a 3 or 4-digit numeric label, where the very last digit just tells you how many zeros to tack on at the end. It's a remarkably simple, highly efficient visual code.
And the cool thing is, this brilliantly illustrates how capacitors have their own similar yet totally distinct labeling systems. For instance, ceramic disc capacitors use a marking system that usually gives values in picofarads along with specific letters that indicate their tolerance range and how they're going to behave when temperatures fluctuate. Again, it is all about incredibly compact communication.
Moving right along to Section 2, semiconductors and microchips. These are, without a doubt, the brains of the operation.
It is wild to see how this hardware evolves over time. In the early days, we relied on discrete components, individual diodes and transistors. And hey, those were a massive revolution all on their own. But eventually, those discrete parts evolved into what we call integrated circuits, or ICs. By figuring out how to pack literally millions of microscopic transistors into a single black rectangular package, we went from building very simple switches to creating components that are capable of complex computation, memory storage, and fully automated control. It's just mind-blowing.
Now, before you run off and start designing with transistors, here is a highly specific, super practical engineering tip straight from our source. The text explicitly warns that the current gain of a bipolar transistor, which engineers refer to as HFE, is incredibly unpredictable. We're talking wildly variable anywhere from 50 to 500 even within the exact same component family. Plus, it fluctuates based on ambient temperature and collector current. So the absolute crucial takeaway here, never build circuits that rely on highly specific HFE values to function, because I promise you your real-world circuit will almost certainly fail.
Okay, let's jump into Section 3, optoelectronics and sensors. This is all about giving our circuits some actual senses.
Basically, optoelectronics bridge the gap between raw electromagnetic energy, like light, and electric current. Some devices, like your standard everyday LEDs, take electrical current and emit physical photons for illumination. But others, like photoresistors and solar cells, do the exact opposite. They capture incoming photons from the physical world around us and convert them back into electrical signals that our circuit can actually understand and respond to.
But light is really just one sense. And that brings up a pretty compelling question. How does a digital electronic circuit actually go about smelling something like smoke in the air, or feeling the sudden presence of a hazardous gas? Well, let's take a look at the ingenious mechanics behind how this actually works.
Let's take the ionizing smoke detector, which you probably have sitting up on your ceiling at home right now. Inside that little plastic shell, there's a tiny source of ionizing radiation, usually a speck of americium. This source creates a steady, microscopic stream of ions that flow continuously to a detector plate. Think of it like an invisible electrical tripwire. When physical smoke particles enter that chamber, they literally block that stream of ions. The circuit instantly senses that drop in electrical current and bam, triggers the alarm. It is just a perfect, life-saving fusion of physics and electronics.
And the crazy part is, we have specialized sensors for almost everything nowadays. Take the MQ4 gas detector, for instance. It doesn't use radiation at all. Instead, it contains a tiny little heating element and a very specific chemical catalyst. When it gets hot, that catalyst actually reacts to the presence of methane in the air. And it's incredibly sensitive, capable of detecting methane down to a mere 200 parts per million. By changing its own electrical resistance based on that specific chemical reaction, the sensor effectively smells the gas and fires off a warning to the microcontroller.
And that brings us to our final stop, Section 4, the inventor's workbench. It's time to start putting it all together.
So the absolute crucial point here is, you just can't build great electronics without having the right physical tools. Our source material gives us a pretty definitive, no-nonsense checklist for a proper setup. Beyond the obvious stuff like a good soldering iron and a reliable multimeter, you are absolutely going to need precision needle-nose pliers and sharp wire snippers. You'll definitely want a solder sucker to fix your inevitable mistakes, trust me on that one, some solvents for cleaning things up, and clip-on heat sinks. Those are lifesavers for protecting your delicate active components from burning up while you're trying to solder them into place.
And hey, speaking of mistakes, when you finally power up your newly invented, beautifully soldered circuit for the very first time, it probably won't work. Honestly, that is completely normal. The textbook actually provides this incredibly dense diagnostic flowchart for exactly this scenario, which we've distilled down into a very actionable 4-step checklist. Step 1, always check the absolute basics first, power and fuses. Step 2, look for loose connections or, components you accidentally plugged in backward. Step 3, literally use your nose and your fingers. Are there any burning smells? Is a component getting dangerously hot? And finally, step 4, if all else fails, logically isolate the circuit into smaller, bite-sized areas so you can hunt down that bug.
You know what's really fascinating, though? It's seeing how our ultimate troubleshooting tool, the mighty oscilloscope, has evolved over the years. An oscilloscope is basically magic. It lets you actually visualize the invisible electrical signals as they move through your circuit over time. You can go from using a vintage $30 Ecoscope running at 10 megahertz, which, by the way, is still fantastic for basic audio projects, all the way up to a massive, modern, cutting-edge 6 gigahertz beast used by professionals to debug high-speed digital systems. The point is, the tools scale right alongside your ambition.
Wow, we have really covered some ground today. We've journeyed all the way from the absolute basics of reading a resistor's tiny color bands through the complex logic of microchips into the real-world physical senses of chemical detectors and all the way to equipping your very own workbench. You now have the foundational blueprint of practical electronics for inventors. So the only question left, and it is definitely the most exciting one, is this: what are you going to invent? Thank you so much for joining me on this explainer, and I genuinely can't wait to see what you build.